So, hello everyone, welcoming you to Shorup's classes. Today we are looking at the General Economics Paper 1 of IES 2022 and at question number 6. So, consider an economy consisting of two consumers, one producer, one ordinary good, and one public good, and one primary factor. Show the Pareto optimality conditions are not valid for the public good. Okay, so let us just have the setup first. So let us say that my two consumers that we are looking at are labeled as consumers A and B, and the one ordinary good that has been mentioned. By ordinary good, we mean the private good over here. Let us say that that good is X, and the public good that we are to mention, let's say it is G. And the primary factor of production is labor. Is L. And let us say that in this setup, the given endowment of labor is L bar. L bar. Now, before actually getting into the solving part of it, we are told to show that the Pareto optimality condition are not valid for the public good. Now, if you remember that if we had, let's say, two private goods X and Y, then how did the Pareto optimality condition look like? If you can just have a small recap of that. So, let's say we had two private goods X and Y and two consumers A and B. Then how did it look like? So for the consumer's equilibrium, it was marginal rate of substitution of agent A has to be equals to the marginal rate of substitution of agent B. For producer equilibrium, marginal rate of technical substitution between labor and capital for good X should have been equals to marginal rate of technical substitution for good Y. Correct? And how did the grand optimal therefore look like? It basically looked like the overall MRS should have been equals to the marginal rate of product transformation. This is the condition which we have encountered in our studies of general equilibrium, and this is the Pareto optimality conditions. So now basically what we are told that in case of instead of two private goods X and Y, if we have one private good and one public goods, the optimal condition is not this, it is going to be something else. So clearly if we can obtain what exactly the optimal solution will be in this case, then we can compare and check what we are getting over here. So now before actually getting into that, so let us first specify a few more details. So let us say that the production functions are as follows. So the production functions are the amount of X that will be produced will be equals to amount of X that is distributed to both of them. That will be a function f, which is a function of Lx, and g will basically be a function h of the Ly, such that Lx plus Ly is, sorry, rather than y, if I can mention that as LG, that will be easier. So labor in sector G. So LX plus LG is basically L bar. What does that mean? That means instead of LG, because LG, LX plus LG is because it's always L bar. So determining one of them can easily determine the other. So LG can be easily written as L bar minus LX. So G equals to H of L bar minus LX, right? And the utility functions can be now as follows. Utility functions. Utility of agent A is a function of the amount of X that he consumes and the amount of public good G that he consumes. And similarly, utility function of agent B will be amount of X that he consumes, xb, and the public good. Note that the very nature of the public good is such that both the agents will consume the same amount because they have equal access to the public good. So how is the optimization problem set up? We fix the utility of one of the agents to a particular level and try to maximize the utility of the other agent subject to all possible constraints. So what do we try to do in this case? Let's say we'll try to maximize UA, which is a function of XA comma xg, subject to fixing the utility of agent B to a fixed level UB bar, and what are the other constraints? The total amount of demand for good X, XA plus XB should be equals to the production of good X, and the production of G has to be demand for G has to match with the production of G. So this is what it is. So what are my choice variables in this case? If you can just have a look at it. You'll try to find out the optimal XA, XB, G, and LX, because LG will automatically be determined. So what do? We'll try to set up the Lagrangian expression to solve this. So, so the Lagrangian will look something like this. You are trying to maximize this function UA, which is XA plus G, subject to the first constraint, which is lambda times UB bar minus UB of XB comma G. So this is the first constraint. The second constraint is plus mu times XA plus XB minus f of Lx, plus the third constraint, so gamma times G minus h of L bar minus Lx. Okay, so this is the Lagrangian expression that we are required. So given the first choice variable is XA, so I'll differentiate this with respect to XA and set it equals to 0. So what do we get? We basically get del UA by del XA. So there's the marginal utility of agent A from good X. So second term will not contribute, plus mu is equals to 0. This is equation number 1. Second, del pound by del XP should be equals to 0. So that will be lambda times minus of del UB by del XP plus mu is equals to 0. So this is equation number 2. Next, del pound by del G is equals to 0. So that will be del UA by del G. So that is the marginal utility from the public good. The second term will also contribute. So minus lambda del UB by del G over here. The third term will not contribute. The fourth term will contribute. plus gamma is equals to 0. So that is equation number 3. And the fourth one is choosing the optimal amount of labor. So del pound del Lx is equals to 0. So the first and the second terms will not contribute. So this will become minus mu times del F del Lx, and this will be your minus gamma times del H by del Lg into minus 1. I hope these calculations are pretty clear. The last expression has been obtained via chain rule. Okay, so these are the four equations that we have got, and we can easily calculate it. So let's have a look at how we are going to do that. So your let's have a look at equation number 4. It gives us some interesting things. So minus mu times, what is del f del x? It is the marginal product of labor in sector X, plus gamma times the second term, del A is del G. So it's basically the marginal product of labor in sector G. So that is equals to 0. So gamma times MPL in G is equals to mu times MPL in X. That means if I take a ratio something like gamma by mu, then that will be your marginal product of labor in sector X divided by marginal product of labor in sector G. Some kind of expression like that. And now look at this thing. So this is the equation number 4 that we have solved. There are a few interesting things that we can get from equations 1 and 2 as well. So from equation 1, I'm just rewriting it once so that it's easier for us to understand. We have del UA by del XA plus mu is equals to 0. That means del UA by del XA will be equals to minus mu. And check this part. So del UA del XA is basically marginal utility of agent A from good X, and that is minus mu. And if you look at equation 2 over here, if I can just scroll up a little bit, yeah. So that is lambda times minus lambda, basically del UB by del XB plus mu is equals to 0. That means minus lambda. So del UB by del XB is marginal utility of agent B from good X is equals to minus mu. And if you replace the value of minus mu over here, so minus lambda times marginal utility of good X by agent B, marginal utility of agent A is equals to, sorry, it will be in the RHS. My mu A of X. Okay. So now using equation 3 that we have, so that's basically your del UA by del G minus lambda times del UB by del G plus gamma is equals to 0. So what we can do is that we can simply divide by mu on both sides, so we get this. Okay, and then we can just shuffle sides maybe. So this will be minus of 1 by mu del UA by del G plus lambda by mu del UB by del G is equals to gamma by mu. So now if you look at it, what is minus mu? And this putting it, del UA by del G is the marginal utility from the public good G divided by the marginal utility of agent A from private good X plus the term in bracket is the marginal utility of agent B from public good G divided by lambda by mu is 1 by mu B, so mu B of X, and this side is basically marginal product of labor in sector X divided by marginal product of labor in sector B. So this is basically the first term is the marginal rate of substitution of agent A between goods G and X plus marginal rate of substitution of agent B between G and X equals to this, not exactly, but we can interpret it as the marginal rate of product transformation given the setup that we have. So this is the Pareto optimal criteria for public good. Now clearly if you look at this, so this is the optimal condition, Pareto optimal condition. If I can just compare with what I had written in just early this part, the MRS should be equals to MRPT. Now this is not the case. So just comparing for private goods, what did you have? MRS of both the agents are equal at optimal, and that is what we represent it as MRS, and hence we get to the grand optimal as MRS equals to MRPT. But in case of public goods, you have to aggregate all the MRS. So that is basically MRS of A plus MRS of B. That will add on to give you the MRPT. This is the optimal condition. And hence, the public good criterion doesn't satisfy the private good criterion, and hence they are not the same, or as they have told us to prove in the question, that the Pareto optimality conditions are not valid for the public good. So this was the Pareto optimality condition for the private good, this one, which is not valid for the public good, because we have worked out and see that the two expressions are not the same. That's it. Thank you.